when Donut Lab released the results of their 100 degrees Celsius thermal test. Most of the conversation focused on one dramatic claim: the battery survived extreme heat. But the most important detail wasn't the temperature itself. It was the fact that the pouch seal failed. The cell visibly swelled. The internal vacuum was lost. And yet the battery continued to operate normally afterward. That mechanical failure may tell us far more about what's actually inside the cell than any marketing headline about energy density or cycle life. Before we dive in, don't forget to hit subscribe and support the channel. Your encouragement keeps us motivated to create even more high-quality content. To understand why, we first need to examine what happens mechanically to a pouch cell at elevated temperatures. A standard pouch battery is built using a laminated aluminum outer layer bonded to a polymer inner lining, typically polypropylene, with a polyolefin-based adhesive holding the layers together. That adhesive generally softens or melts somewhere between 80 and 90 degrees Celsius. At 100 degrees Celsius, seal degradation is not surprising. The laminate loses structural integrity, internal pressure changes, and the pouch can swell or lose vacuum. In other words, the swelling itself is not extraordinary. It is mechanically predictable. What matters is what did not happen. The cell did not ignite. It did not violently vent. It did not appear to suffer catastrophic electrochemical failure. And that is highly unusual if this were a conventional lithium-ion battery using standard carbonate-based liquid electrolytes. Most lithium-ion cells used in electric vehicles rely on organic carbonate solvents, such as ethylene carbonate and dimethyl carbonate. Dimethyl carbonate, for example, has a boiling point around 90 degrees Celsius. At 100 degrees Celsius, vapor pressure rises significantly. If the pouch seal fails under those conditions, volatile flammable vapors can escape. Combine that with oxygen and elevated temperature, and you have the necessary conditions for combustion. This is precisely why major manufacturers like LG Energy Solution and Samsung SDI do not operate commercial lithium-ion cells anywhere near 100 degrees Celsius in normal testing regimes. The safety risks are substantial, yet in this case, despite the seal compromise and visible swelling, the Donut Lab cell continued functioning and was able to accept charge afterward. That strongly suggests that whatever electrolyte system is inside does not behave like a conventional flammable carbonate liquid. This is the first major conclusion. The swollen seal does not prove the battery is revolutionary, but it significantly weakens the idea that it is a standard liquid lithium-ion architecture. If it is not a typical liquid electrolyte system, what could it be? One plausible explanation is that the battery uses a polymer-based or gel polymer electrolyte. In such systems, a polymer matrix hosts the conductive salt, and solvent content is either immobilized or minimized. These systems dramatically reduce volatility and flammability. If the pouch seal fails at 100 degrees Celsius, there may be no significant vapor pressure spike and no flammable solvent release. The cell could continue operating even with compromised packaging. Polymer systems also do not require the extreme mechanical pressures associated with ceramic solid-state batteries. In the reported test, the applied pressure was under 1 megapascal, far below the multi-megapascal compression typically required for dense ceramic solid electrolytes. That detail makes a fully ceramic solid-state architecture less likely. Another possibility is the use of ionic liquid electrolytes. Ionic liquids are known for extremely low vapor pressure and high thermal stability. Unlike traditional carbonate solvents, they do not readily evaporate or ignite at 100 degrees Celsius. A cell using ionic liquids could plausibly survive pouch compromise without entering thermal runaway. However, ionic liquids typically introduce higher viscosity and distinct resistance temperature characteristics. The observed moderate drop in internal resistance with temperature does not clearly confirm this scenario, but it does not rule it out either. The third possibility is more disruptive. The battery may not be lithium-ion at all. Donut Lab has described their technology as lithium-free. If true, that points toward sodium-ion chemistry. Sodium-ion batteries can exhibit higher thermal stability depending on electrolyte choice and interfacial chemistry. Their solid electrolyte interface behavior differs from lithium systems, and certain sodium architectures are more tolerant of elevated temperatures. if the cell uses a sodium-layered oxide cathode, a titanium oxide-based anode, and a polymer or solid sodium electrolyte within a carbon nanotube conductive framework. That could potentially explain the voltage profile, the high-temperature survivability, and the absence of flammable behavior after pouch failure. However, even if the system is sodium-based, another challenge emerges. Leading sodium-ion technologies currently achieve energy densities in the range of 160 to 175 watt-hours per kilogram. A claim of 400 watt-hours per kilogram would represent a dramatic leap beyond what has been publicly demonstrated. The seal swelling behavior tells us something about safety and materials. It does not automatically validate extraordinary energy density claims. What the swollen seal truly reveals is this. The internal chemistry is unlikely to be a standard liquid lithium-ion system. It may not even be a conventional ceramic solid-state battery. Instead, it could represent a hybrid architecture, polymer-based, sodium-based, or using a non-volatile electrolyte system that blurs the line between solid and liquid classifications. The term solid-state in marketing often creates an image of a fully solid ceramic electrolyte replacing all liquid components. But in practical battery engineering, many systems exist along a spectrum between fully liquid and fully solid. Gel polymers, composite electrolytes, ionic liquids, and semi-solid matrices all occupy intermediate territory. The swollen seal event suggests that Donut Labs' battery may reside somewhere in that middle ground. Ultimately, the pouch swelling does not expose fraud, nor does it confirm a breakthrough. What it does is narrow the possibilities. A conventional flammable carbonate lithium-ion system would likely not have survived the conditions described. The fact that this cell did survive points toward a fundamentally different electrolyte design. The real question moving forward is not whether the seal failed, it is whether the underlying chemistry can deliver on the performance claims at scale. Surviving 100 degrees Celsius without ignition is impressive from a safety standpoint, but safety alone does not guarantee manufacturability, cost efficiency, or sustained high energy density over thousands of cycles. The swollen seal may not prove what the battery is, but it strongly suggests what it is not. And in a field where small material details define billion-dollar outcomes, that distinction matters. And of course, everything we've discussed so far is just our analysis and speculation about Donut Labs' experiment. What do you think? Share your thoughts in the comments below.